Okay, welcome to our last presentation on determining eigenvectors. In this case, we're going to focus on repeated eigenvalues, but we're going to just consider repeated up to, let's say, twice. Now, I hope now you're mastering the whole process of calculating eigenvalues and eigenvectors. So now our focus will be only how to handle these repeated nodes. So say we're given a matrix A, and then we need to find the eigenvectors. So this, our initial step again, we'll start at A minus lambda identity. That's our characteristic polynomial. This will come out as determinant of 3 minus lambda minus 2, 2 minus 1, 5 minus lambda minus 2 minus 1, 3 minus lambda. Now, at this stage, I'm not going to go through the tedious calculation of this determinant. I'll give the polynomial and you can double check it yourself. There may be some numerical errors or signs that you can check for your own practice, but I expect you to get something more or less like this. That will be a characteristic polynomial, and for this you really need to have a well-developed skills in factorizing polynomials of degree higher than 2. Then setting up an equation, which is our second step. We have lambda cubed minus 8 lambda squared plus 20 lambda minus 16 equals to 0. Like I said, I'm not going to solve this, but we have already gone through the calculations. For now, just to save time, I'm going to tell you that the eigenvalues you must expect here is 4 and 2, and the 2 happens to be repeated, otherwise twice. Then let's start by getting the eigenvectors. Let's say finding eigenvectors. So for now, let's say 1 for lambda equals to 4. Now, for lambda equals to 4, doing this kind of calculation, we have a matrix here. 3 minus 4 to give us minus 1, minus 2, 2, minus 1, then 5 minus 4, that will give us 1, and minus 2, last row will be minus 1, 3, minus 4, which is our lambda, and of that there. Then this to multiply by a 3-component vector E11, E12, E13. and this must give us a 0 vector. In this case, a vector in R3. Okay, so the next thing is to now take the equivalent equation, system of equation, which is minus E11 minus 2E12 plus 2E13, and this is equals to 0, then minus E11 plus E12 minus 2E13 equals to 0. So I hope you can see that in all this transforming this to a system equation, your knowledge of multiplication of matrices is very essential. Then we've got minus E11 plus 3E12 minus 4E13 equals 2. This is our last equation, equation number 3. Now we need to solve this equation. In this case, if we say equation, let's say equation 2, we subtract equation number 3. In other words, we're solving this by kind of elimination. We're getting minus 2E12 plus 2E13 equals to 0, which will take us to the conclusion that E12 is equals to E13. And then substituting this in equation 1, now substituting in 1, we have minus E11 minus E12 equals to 0, which takes us to concluding that E11 is equal to minus E12. Right. So from there, we can now build our eigenvector, our first eigenvector for lambda equals to 4. In this case, the eigenvector will be E1. As you can see here, E11 and E12, they are equal, but E11, so E12 and E13 are equal, but all E11 is got and E12 got opposite sides. So we can take this to be 1 minus 1 minus 1. These two are equal from there. These two have got opposite signs. Then multiply by the scalar alpha. Then we can write there that alpha scalar. So that's our first eigenvector. Vector. Now, next we need to now look at lambda equals to 2. Now for lambda equals to 2, the repeated root, let's write here equals to 2 twice, because we've got to make sure that we've got 3 eigenvalues. So this one is repeated twice. Now this kind of matrix will come out this way. We're going to have 3 minus 2, 1, minus 2, 2, minus 1, 5 minus 2, we get 3. Here minus 2, minus 1, 3, minus 2. Okay, then multiplied here by eigenvector number 2, component 1, eigenvector number 2, component 2, eigenvector 2, component 3, and again this is going to give us our 0 vector, which will be 0, 0, 0, 0. This expression, you mustn't lose sight that this is the expression which we started with, which says lambda minus a minus lambda I multiplied by the eigenvector give us 0. Then this circles to a system of equation which would be E21 minus 2E22 plus 2E23 equals to 0. Then minus E21 plus 3E22 minus 2E23 equals to 0. That being equation number 2. Last equation is going to be minus E21 plus 3E22 minus 2E23 equals to 0, and that. I hope you can see that to get this system equation, I didn't mention this, but you can see that we are actually using multiplication and also using quality of matrices. So once we multiply here, this is a 3 by 3 multiplied by 3 by 1, and this is a 3 by 1. So you get a 3 by 1 matrix here. Then you taking 2 matrices to be equal, then the result, and that's this is system equation. So now, solving this system of equation, one thing which is clear here, we'll see that from the first equation, equation number 1, we'll say from equation number 1, we can state that minus E21 is equals to so this is from equation number 2, sorry, number 2. From equation number 2, minus E12 is equal to minus 3 E22 plus 2 E23. And on the other hand, we've got E21 equals to, so this is equivalent to say E21 is equals to 3 E22 minus 2 E23. That is same thing. And now, what does this mean? It means that our second component of the vector, sorry, our first component of the vector depends on E1 and E22 and E23. So then, to write this vector number 2, we can actually write it this way as 3 alpha minus 2 beta, and then you can now choose alpha and the beta to be parameters. So we've got this vector like this. So now it's here, we just chose to replace E1, E22 and the E23 by alpha and beta. Now, where does this take us to? So this takes us to, as you can see now, we can say E2, this vector, is actually a vector like this. Let's first of all write this vector in a suggestive way as 3 alpha minus 2 beta, alpha plus 0 beta, 0 alpha plus beta. I hope it's clear to everybody that this is exactly that vector. With the way I'm writing this way, I'm writing it in a suggestive way so that we can understand what follows there. What happens now, we can see this as 2 column matrices which are being added. Which matrices? In this case, you can take a matrix in terms of alpha, which is 3 alpha, alpha, and 0. And this column matrix being added to plus minus 2 beta, 0 beta, and beta. Now simplifying this, using let's say you can take alpha, this is 0 alpha, 0 is alpha is a scalar here and beta is a scalar here. You can write this as alpha (3, 1, 0) plus beta minus 2, 0, and 1. Now, actually, here we have got 2 vectors. In this case, our representative vectors will be 3, 1, 0 and minus 2, 0, 1, and their scalar multiples are going to be eigenvectors. So now, representing the 3 eigenvectors, we would say we've got the family of eigenvectors will be, let's write this 3, 1, 0, and another vector will be minus 2, 0, 1, and then for 4, we had the vector 1 minus 1 minus 1. So we have here 1 minus 1 minus 1. Okay, this set of vectors is what you can call a representative family for all the eigenvectors corresponding to the matrix given. And there's something interesting here which I want you to check in relation to what we did before. I would like you to check whether this set of vectors is linear, independent, or is linear dependent. Your results here will actually extend your theory on in as far as knowledge of eigenvectors is concerned. So in our next discussion, we're going to, apart from your results here, to add on the theory of eigenvectors and eigenvalues. What is left now is for you to go to your textbook and take examples and solve for find eigenvalues, find eigenvectors, and you can do this kind of testing and see what kind of general result you can come up with. At the moment, I would like to say thank you for listening.